Okay, to follow up with Unit 4, Part 3, Lesson 1, we're going to take a look at this ladder problem. We've got an 8-foot tall fence that runs parallel to the wall of a house at a distance of 5 feet. Find the length of the shortest ladder that extends from the ground over the fence to the house. Well, there's a phrase, shortest ladder. I think this is going to lead us to an objective function. Assume that the vertical wall of the house is 20 feet high and the horizontal ground extends 20 feet from the fence. Now, what these two numbers at the end are doing are giving us a limitation or a constraint on our domain. It doesn't actually give us a constraint function. I'll talk about that as we identify our solution. The constraints that we're actually going to be working with are this value here, that the fence is 8 feet tall and that it's at a distance of 5 feet from the house. So a sketch might be helpful here. If this box is kind of a side view of the house and this vertical line represents the fence, we're being told that the fence is 8 feet tall and it's 5 feet away from or parallel to the side of the house. And so what we have to do is find a ladder that has the minimum length that will reach this house and still go over the fence and essentially come in contact with the ground down here. Now certainly I could draw a ladder like this that reaches over the fence and bumps up against the house. It would be very unrealistic for that to be the case. And so that's where this 20-foot horizontal ground extension comes into play. They're just reminding us that we only have 20 feet of space out here. And so that's going to limit our position of this ladder just a little bit. Now, hopefully you also recognize that by finding another position for this ladder to rest is going to reduce the length of the ladder considerably. And you might even guess that the ideal position is resting the ladder at the very top of the house. Now, resting it at the top of the house is good to consider because we can't have the ladder, even if we wanted to, we can't have the ladder extend up above the house because then it has no place to rest there either. And that too is part of the reason why we have this additional piece of information that the house is 20 feet tall. So I'm going to use this bold line here just to place a ladder in position and also to emphasize a right triangle that's formed by the ladder and the base, I should say the side wall of the house and the floor, or the ground. Additionally, I'm going to emphasize this triangle that's drawn right here. And this triangle is similar in shape to the blue one because it does have 3 congruent angle measures. And from our geometry days, we should recognize that triangles with 3 congruent angle measures are therefore at least similar. And because they're similar, their side lengths are going to be proportional. And that's actually going to be one of the most helpful components of this problem. So before we get into that, I'm going to start by listing some objective function here. We want the shortest ladder. Well, I'm going to call the ladder length C, and that's the hypotenuse of a right triangle. So therefore, the objective function that I think we should work with is C squared equals A squared plus B squared, where A and B are the side lengths of the blue triangle. Our constraints, therefore, must relate A and B to one another. And so what we don't know for certain is the position where this ladder is going to rest on the ground. And since this position could slide in either direction, to find the shortest ladder length that still meets the requirements, I'm going to call the distance between the fence right here, that was right here, and the base position of this ladder, I'm going to call that X. I'll choose a different color just to make that stand out a little bit. So X is the distance where the ladder potentially could slide and settle at, the base of the ladder that is, and 5, of course, is the distance to the wall. So with that known, we could say something like this, that A, the base of the blue triangle, is simply equal to X plus 5, whatever X is plus 5. Now, B, on the other hand, that's a bit harder to establish because it might be thought that B has to be 20, but remember, as this ladder position here, as this ladder slides to a different position, then the height of the blue triangle changes. We know that the height's maximum is going to be 20 because that's the top of the house, but as far as the actual B value, we don't quite know what that is. And this is where the similar triangles come into play. I know that the proportion of A to B is going to be the same as X to 8. A being the base of the blue triangle and B being the height of the blue triangle must be equivalent to the ratio of the base of the orange triangle to the height of the orange triangle. Now, to make this a little bit more useful, I'm going to switch A back to the definition that I gave back here, this x plus 5 for the time being. And by doing so, we can cross multiply and divide to isolate the value of B, and therefore we would have a constraint value for our B function. So if we cross multiply, we have B times x equals 8 times x plus 5. And then we can immediately divide by x to isolate B. So essentially B is equal to 8 times x plus 5 divided by x. And if we distribute in that numerator, we'll end up with an expression for our B constraint to be 8x plus 40 divided by x. And you know what, in actuality, I think I'm going to leave that as x plus 5. I have a hunch about the next step here. Leaving this in factored form might be more helpful. Okay, so we actually have enough information, I think, to solve this problem now. We have our objective function, and we're going to try to minimize the c value. We can rewrite the objective function in terms of a single variable. Right now it's written as two variables, but we can write it as a single variable x as long as we rewrite a and b using the constraints that we've identified. So let's see what happens. We've got now c squared equals, we could say x plus 5 quantity squared, that's our a value, plus 8 times x plus 5 quantity divided by x squared. Now here's why I think leaving it in factored form might be beneficial. Again, I'm going to leave this one in factored form as well. If I were to square this fraction, essentially everything becomes squared because it's a product and quotient. So we end up with 64 times the quantity of x plus 5 squared over x squared. And an old algebraic trick lends itself, becomes visible at this point. This x plus 5 squared is a common factor to these two terms that are separated by the addition sign. And so if I write x plus 5 quantity squared as a common factor, and I factor it from this term, I'm left with the number 1. And if I factor it from this term, I'm left with 64 divided by x squared. And I don't know, I just have a hunch that maybe computing the derivative in terms of this expression might be a bit more manageable than computing the derivative in terms of this expression over here. Clearly, we would need the quotient rule in this case, whereas over here, we've got a bit of a shortcut where we can find the derivative of a single fraction. And so if we find the derivative in terms of x on both sides of the equation, or apply the derivative, if you want to call it that way, we would see something like this. Well, the derivative of c squared is going to be 2c, but since the c and the x variable differ, we have got to multiply by the differential dc dx, which is fine because this is the value we want to be set equal to 0, and it's ultimately going to turn the left side of the equation equal to 0. We will need the product and chain rule on this right side, so let's get to it. The derivative of a product of functions is the derivative of the first function, which this first function is going to be 2 times x plus 5 to the first power times 1. That's because it's the derivative of the outside function, keeping the inside function as it is, and then taking the derivative of the inside function and multiplying it. We don't really need this multiplication of 1 or the exponent of 1, so I'm going to erase those. So this is the product, I'm sorry, this is the derivative of the first function, and we multiply that by the second function, untouched. And to that we add the first function times the derivative of the second. Now the second function's derivative, of course, this one, derivative of 1 is 0. And the derivative of 64 over x squared, well, we'll multiply the 64 times 2. We change its sign, and we now have negative 128. And then we increase this exponent by 1. We increase the exponent by 1 in the denominator because that would be the same as taking that negative exponent that it represents and reducing it by 1 with our power rule. And again, the ladder length will be at an extreme value, either a maximum or a minimum, when the derivative is equal to 0. So if that derivative is equal to 0, then this whole left side of the equation is equal to 0. And we've got a bit of algebra to run through over here on this right-hand side to make this solvable, because I'm thinking, again, the left side is going to be equal to 0, and we've got to find what number on the right can be replaced for x to make the entire expression equal to 0. So what I'm going to do first is I'm going to recognize that x plus 5 is again a common factor, and so I see that here in this first term and one of those x plus 5s here in the second term. So I'm going to factor that out, and I'm going to show what's left behind. So we have 2 times 1 plus 64 over x squared plus another copy of this x plus 5 times negative 128 over x cubed. So on the left side, we've got an expression that's equal to 0, and on the right side, we still have this x plus 5 common factor, and I'll probably distribute and see if we can combine terms down to maybe a single expression. It's likely going to be a fraction because of these denominators, but let's see what we can get. So I'm going to call this distribution, we'll call that 2 plus 128 over x squared. And with this distribution, x and 5 get distributed to this expression. So x times negative 128 over x cubed, well, that's nice because we have negative 128x over x cubed. Now, this x in the numerator can cancel with one of the x's in the denominator, and we now have x squared. And 128x squared added with a negative 128 over x squared will cancel. So that's nice. And this last distribution, 5 times negative 128, is 640. So we now have a negative 640 over x cubed. Now I can create a common denominator of x cubed pretty easily if I multiply this guy by x cubed over x cubed. That's a form of 1 that we like. And so now I have 2x cubed minus 640 over x cubed, which would be the same as 2 times x cubed minus 320 divided by x cubed. Whoops, forgot about my first term, so let's get that placed in here. So we have x plus 5 times this fraction and x plus 5 times that fraction down below. Okay, I think we're finally at a point where we can solve, because now I have the product of two numbers that multiply to equal 0, and so that tells me that either x plus 5 equals 0, therefore one solution is negative 5, or this fraction could be equal to 0. Now the only way that a fraction is equal to 0 is if the numerator equals 0. So we're thinking to ourselves, when does x cubed minus 320 equal 0? Well, that would be the cube root of 320. It is worth noting that the expression over here does not exist when x is equal to 0, so that's a critical point as well. But we should also recognize, too, that x, being the position beyond the wall here, has to be greater than 0. We can't have the base of the ladder right here at this position. And x can't be bigger than 20 because of our restrictions too. So that's kind of the domain restriction we were discussing at the very beginning here. So I'm not really going to consider this particular critical point where that derivative doesn't exist. Similarly, I can't really consider this x equals -5 as an option, so I'll just cross it out too, because the base of the ladder can't be -5 feet to the right of this wall. That would actually place the base of the ladder over here, which violates the description of the problem. So it looks like we're dealing with this position as a solution. And if I reach for a basic calculator, and I think the use of a simple calculator here would be appropriate for this problem, I would just want you not to reference the graphing capabilities to bypass our calculus work. But we need the cube root of 320, so that's not going to work. Let's use the nth root command. We want the cube root of 320, and that's about 6.8399. 6.8399 feet. And that falls within our boundaries, if you will, of the problem, where x has to be bigger than 0 but less than 20. It's worth the extra effort to double check that our height b is going to be within the boundaries as well. So we think we know what x is. We're going to say that that's about 6.8399 feet. So just as a double check, if you will, let's calculate the height as it would reach against the house, because this is limited to 20 feet. So 8 times 6.8399 plus 5 divided by 6.8399. Let's check that out. And that results 13.8480. 13.8480. And that's a good sign too, because we're thinking that the ladder is going to reach 13 feet in the air, which is within the dimensions of the house. And we think that it's about 6.83 feet to the right of the fence, which is within our boundary as well. And so all signs are pointing to an extreme value that lands within our boundaries, but let's see if that extreme value is indeed at a minimum point. We need the second derivative in order to do that. So in order to calculate the second derivative, and this is definitely going to be a bit of a challenge, we worked through the second derivative. We ended up setting it equal to 0. I kind of like this format. No, I think the next one's a little bit better. I like this format of the derivative. So I'm going to use that to find our second derivative. Let's just jump over here and clear some things up. Our first derivative, dc dx, or well, let me write it this way. Our derivative with respect to x of c squared is essentially equal to this expression. Now I'm going to consider this x plus 5 as a fraction over 1. And this coefficient of 2, I'm actually going to push it out front. So I'm going to call this 2 times x plus 5 times x cubed minus 320 all over x cubed. And I may even consider this 2 as a coefficient out front. And the reason for rewriting it this way is that it gives me something I think a little bit more manageable to find the derivative of within this grouping bracket here. So if I need the second derivative of c squared, that would be the derivative of the step above. Well, this 2 acting as a coefficient, well, that just drops down. And now I just need to apply the quotient rule and essentially the product rule in the numerator too. So here we go with the quotient rule. The low function, x cubed, times the derivative of the high function. Now this is where it gets a bit challenging because the derivative of this upper function requires the product rule. And so the product rule when finding the derivative of this expression would be the derivative of the first function times the second function plus the first function times the derivative of the second function. Okay. So that's the first part of our quotient rule. We've got low, and then the derivative of the high function. Now we need to subtract the high function times the derivative of the low function. So I'm clearly running out of room. I'm going to cheat a little bit with my electronic ink here. Slide this down. Okay, so low d high minus the high function, x plus 5 times x cubed minus 320 times the derivative of the low function. So this is low d high minus high d low. The low function's derivative is 3x squared. And so now we've got low d high minus high d low over low, x cubed squared. And some cleaning up here would be beneficial. I can't just substitute x in place here and determine the polarity, the positive and negative results for each of these expressions yet, because we've got some terms that are separated by addition signs and subtraction signs. And that just, that trick that we've been using along the way just won't work here for that reason. So I'm going to call this 2 times, I'm going to leave this x cubed alone for the time being, and in this interior I've got x squared minus 320 plus 3x cubed plus 15x squared. And you know what? I think what I would do, since I've already mentioned it once before, we're using a calculator, a simple calculator to or a scientific calculator to calculate this value for x. Why don't we just substitute this number in place of this expression and see what we get? And you'll have to take my word for it because I typed this off camera. I ended up getting 8.6784, which is greater than 0. And when our second derivative is positive at this location, we're concave up. And if the graph is concave up while the first derivative is 0, we have found a minimum. Well, clearly, I think you found the problem that's going to be worth a significant number of points on our test. And there's a lot of work here. Clearly, a calculator is preferred in this work. I suppose we could have spent some extra time simplifying this second derivative if we needed to, but in all honesty, I think it's fine the way it is. Now, we're truly not quite finished yet because we just found x, the position of the base of the ladder. We actually need to calculate the length of the ladder, and we can use our objective function for that. C squared equals a squared plus b squared. And we're going to be using the a and b values from our constraints.